Good morning, students. In today's class, we'll start our unit 2, that is chapter 1, band theory of solids, right? So, first of all, the unit objective, today's our unit objective is that we need to understand the energy bands which are existing in the solids. So, we already had an information regarding what is actually the meaning of solid. So, solid is nothing but it is the combination of closely packed atoms or molecules, right? So, the elements which is having this particular property is known as solids. So, in the unit 1 we had just a brief overview regarding what is actually matter is composed of and the different classification of the matters. We have just discussed the classification of matters. In that we have given importance to the solids. So, why we have given importance to the solids? Because of its engineering importance. So, solids have been classified into two important categories: crystalline solids and non-crystalline solids. So, solids have been classified into crystalline solids and non-crystalline solids. So, crystalline solids is again classified into two subcategories. That is, first one is single crystal, another is the polycrystal. Again, the non-crystalline solid has been also known as the amorphous solid. So, here we just discussed the schematically and geometrically, we just discussed the arrangement of the constituent particles which are existing in the solids, and we have considered certain important parameters, that is what is the meaning of space lattice or crystal lattice, what is basis, and what is the structure, crystal structure. And then with this imaginary concepts, we just concluded that geometrically the structure of the crystal can be drawn in the different formats, and on the surface of the earth we know that we can find different 7 types of crystal systems, and in that 7 crystal systems, depending upon the lattice parameters, they have been classified into different categories, that lattice conditions. So, what is that lattice parameters? A, B, C, alpha, beta, gamma together combine to form the lattice parameters. So, by knowing this lattice parameter, one can understand the exact nature or the type of crystal form or size of the crystal system. So, with this we had learned about the now we had an exact idea that what is actually crystal is composed of, and when we incident the X-rays or neutron beam or an electron beam on the crystals, so we can just study the different properties of the crystal, and the incident of the light ray has been importance signifies the X-ray diffraction. We just studied about the X-ray diffraction, that is Bragg's condition. Whenever we incident an X-ray or any light, so it should it will undergo the diffraction. So, if it is undergoing X-ray diffraction, it should satisfy the condition called Bragg's law that we studied about 2D sin theta is equal to n lambda. So, once if this particular condition is satisfying, then we can study the properties of the crystal, and we have applied some different methods of the X-ray diffraction, and out of which we just discussed about the X-ray diffraction method. There are different methods or techniques to study the properties. So, such as the what we can say powder method or the powder method, and single crystal rotating crystal method, powder method, and so on. So, we just given our concentration on the powder method, and we discuss the powder method with the dB Shearer camera. So, with the dB Shearer camera, we conclude that with different diffracting angles, once one can get the exact structure of the crystal, and the crystal structure signifies different important properties of the given crystal. Now that we have done in the latest section, and this is I'm talking about the chapter 1. So the by means of which we chapter 1 we understood that the properties of the crystalline solids can be known by means of incidenting the X-rays or neutron beam or the electron beam, but we just studied about the incidence of the X-ray beam to analyze the properties of the crystal. So that is about the chapter 1. When we go to the chapter 2, now definitely is the crystal is we talk when we talk about crystalline solid or when we talk about a crystal, so is it possible that this crystal is in the crystal the atoms or the ions or the molecules are exactly arranged in a sequential order? So this is an ideal case, right? We just discussed about the ideal case, but in practically that may be you find the different arrangement of the constituent particles. So now that particular factor or the parameter we just discussed about the defects in the crystal. So defects in the crystal, we need to understand the defects in the crystal. Why? Because now depending upon that defects, we signifies the important parameter called electrical conductivity of the solid. So this is very important aspect. So once if we study about the defects in the crystal, then one can say that we just know the electrical conductivity of the crystal precisely. This is not only one parameter, but different parameters can be analyzed by means of studying the defects in the crystal. So what are the defects we studied in the chapter 2? We just studied about the different defects, and that defects are nothing but what you can say point defect, or we'll call zero dimensional defect. We call line defect, that is called one dimension defect, and there is a surface defect, we call that as a two dimension defect, and volume defect we call that as three dimensional defect. And out of which we have given again we have just analyzed in depth, we have analyzed the point defects. So we just classified that point defects into different categories. So point defects is again classified into vacancy, right? Point defect, vacancy, interstitial defect, right? So these are the few sub-classification of the point defect. And again we had electronic defect that come under the category of point defect, that is called Frenkel and Schottky defect. So, and we already discussed in the previous class the equilibrium concentration. Mathematically we derived that how we can get the Schottky defect value mathematically and how we can get the Frenkel defect value. Now these defects have been studied not only theoretical but also some mathematical calculation has been also done in the chapter 2. Now this is what we studied, and later on we studied about the what you can say dislocation, line defects. So when we talk about line defects, we studied about some dislocations, right? One dimension defect. I'm talking about one dimension defect. So dislocation, screw and edge dislocation. We had an information regarding screw and edge dislocation and Burgess vector. And at last we studied what are the different applications of the defects occurring inside the solids. So now this was the brief overview regarding the unit 1. Now one should know what is actually the energy which is resembling inside the solid. Now that is called unit 2 chapter 1. The chapter 1 deals with the, we'll call that energy as band theory. In order to know the energy of the solid, so we need to understand band theory of solids. So different scientists has given their own views regarding the band theory of solids. So let in this particular section we just understand what is actually the free electron theory. You know, we need to understand first of all there is a theoretical concept which has been given by the two scientists that according to them we'll call this as Drude and Lorentz theory, or we'll just say that the classical free electron theory. So in the classical free electron theory, we just study what we study actually. So what is need of studying this free electron theory? We say that in a solid, electrons can move anywhere These, this assumption was made by the Drude and Lawrence. So, so why we need to understand this? We actually want to know the band theory of energy band which is existing inside the solid. That is our objective in learning the three important topics, that is called free electron theory. Slowly we start with the basic concept assumptions of Drude and Lawrence, and when we go to the next one, that is kronig penny model, and then the last one we'll just study about this origin of energy bands in solid. Now these three important things will make us to understand what is actually the energy band in solid, how the energy bands are existing inside the solid. So now we just go the first aspect, that is called free electron theory. So the free electron theory are actually divided into two different categories, that is called the basic classical free electron theory and the quantum free electron theory. Here we are giving our what you can say, we are just going for a concentration. Our concentration is on the classical free electron theory. So now the classical free electron theory deals with the electron which is moving very freely in the lattice, and it obeys the normal laws of classical mechanics. So now here the electrons are assumed to be having constant potential. What is the meaning of constant potential here? It means that when electron is traveling inside the crystal, so the electron will have a constant movement inside the solid. So right, so later in the section we'll just understand what is actually the quantum free electron theory and what is actually the zone theory, that is called brilliance zone. That is a basis of the band theory. This is based on band theory. So now what is actually the Drude and Lawrence? They have introduced developed this theory in the year 1900. So what they say is that, see, whenever we talk about when we deal with an what you can say physics, when you talk about physics, so physics, how this physics is utilized for an engineering student. So how it has been utilized, we'll go for application point of view. When I say an application, so application of this physics to an engineer, so definitely our main what you can say concentration goes on to the metals. Metals is of a great importance for the industry purpose and for production and manufacturing different devices. So that is a need of studying about the metals. So now, keeping in view this particular aspect, this topic has been introduced to you to know that how the electron move inside the metallic crystal. So when we say, so what the Drude and Lawrence says, let's go for one by one, right? So what they say is that the atoms are composed of all the atoms are all the solids actually composed of different atoms, and each atom is having a central nucleus around which the electrons are revolving. This is a basic concept that you have already been what you can say studying in the lower classes. You studied, right? So the electrons are free to move. Now you can just see the electrons are free to move in all possible direction throughout the metal. So if there is, in the absence of any electrical field, so the electrons move randomly or move making some different collision, and which is with the fixed lattice point or free electron, all the collisions are elastic. Means, what is the meaning of elastic? They will just incident on the walls of the metal, and again they retrieve their path, right? And this particular process will continue, and during this process there will be no loss of energy. And when the external field is applied to this metal which is consisting of free electron, so slowly it will try to drift toward the positive potential, or definitely this aspect will be understood very clearly. So whenever an external electric field is applied to the metal which is consisting of the free electron, right? Metal is a good conductor of electricity, therefore, so when it is happening, so slowly that electron will attracted to the positive potential, and slowly it is drifting toward the positive potential. Since the electrons are assumed to be a, see what they assume that, let us consider the electrons, movement of the electrons are nothing but they are how the molecules move in a perfect gas. So now as if the molecules move in a perfect gas, and thus they obey the we say that since it is a perfect gas, if we have compared with the perfect gas, then definitely they should obey the kinetic theory of gases. So now the classical electron theory, also free electrons should obey the Maxwell-Boltzmann statistics. So now this is why it is obeying Maxwell-Boltzmann statistics. Why? Because the movement of the electron, the velocity of the electron can be calculated. We can calculate by Maxwell-Boltzmann statistics. Now this was the first, see, classical free electron theory. So once we can just have again the important postulates. What they say that the metal is consisting of, metallic crystal is consisting of free electrons. They are moving from one end to the another, and they are colliding with the with each other. That collide with the collision, therefore there will be no loss in the energy. And as if you apply some external field, so what will happen, these free electrons are definitely drifting towards the positive potential. And whenever we talk about free electrons, these free electrons are considered to be the concept of gas, perfect gas, where the molecules are free to move as if they constitute the electron gas. And as it is a perfect gas compared with the perfect gas, definitely they will obey the classical electron theory. Now this was an assumption which has been made by Drude and Lawrence. So we need to understand, wow, what are the basic defects. Defects have been what is implies, right? What are the defects which has been implies, and what are the merits or what are the applications from this classical free electron theory due to their assumptions, right? Some what you can say defects have been taken into consideration, and some applications are also there depending upon their assumptions. So now what are the, first of all we'll discuss about the merits of classical free electron theory. So now it is used to verify the Ohm's law. Now we say that Ohm's law V is equal to IR is there, and these Ohm's law V is equal to IR, right, has been verified by means of this free electron theory. So it's actually this is ELCTR, right, electron. The electrical and thermal conductivities of metals can be explained. So the electron and thermal conductivities of the metals can be explained, and it can be derived with the Weidmann-Franz law. So what is the Weidmann-Franz law? We just come to know, and it is used to these classical, depending upon this classical free electron theory, one can know the optical properties of the metal, right? So practically it is these are the applications of the classical free electron theory. And so what the defects which have been occurred in the free electron theory is according to this theory. So see, we just said that in the merits it is used to derive the Weidmann-Franz law, that is K by rho T is equal to L is a constant for all the temperature, but this is not true. So this particular condition, see, we say that this condition is nothing but this is called Weidmann-Franz law, right? So now depending upon this, which is telling us about the conductivity of the metal, and this is exactly applicable for the particular high temperature, but it is not true to at low temperature. So low temperature you don't find this particular law is what you can say the holds good. So now theoretically the specific heat of the metal is not what you can say, it doesn't match with the experimental value, and this theory is also cannot explain the superconductivity and different effects, Compton photoelectric effect and black body radiation. Now this is a main drawback of this classical free electron theory, and this theory is applicable, right, for macroscopic right level. Now this is one of the important drawback. Why? Because when we talk about metal, when you talk about electron, when you talk about atoms, now these are microscopic particles, submicroscopic you can say, because we cannot see exactly the on the neck, with the naked eye we cannot see the electrons, right? Now this is what the important what you can say merits and the demerits of the classical free electron theory, which has been given by Drude and Lawrence, or we say that is called classical free electron theory. Now when we go to the next important topic, that is about the Kronig-Penney model. So what the Kronig and Penny, they again, the scientists, they have given their own view that what is happening when the potential inside a metallic crystal. So how this potential is varying with respect inside the crystal when the electron is moving, how the electrons are moving. We already know that in intermediate level the electron, both it behaves as a particle nature and also it behaves as a wave nature. So now, depending upon that particular concept at a particular instant, so it will behave as a particle nature, and after a particular instant, the second at the particular level, so it also behave as a wave character. So now, so what the Kronig and Penny assume that they actually, the movement of the electrons are nothing but they are a sequential order of square wells. Instead of, see, what is the assumption made previously, that the potential is constant, the movement of potential is constant here. So what the assumption has been made, but the Kronig Penny say that the movement of potential is in the form of the square wells. You can just see this is a form of square wells. Now these square wells, theoretical concept, see, this is origin, the a, and this is what twice 2a, where a is nothing but the lattice constant of the given crystal. So we already told you that what are the lattice constants. A, B, C are the lattice constant, and you will find that the movement of the electron will be in the form of a square well. Now this was the assumption which has been made by the Kronig and Penny, and this is very, very important aspect which has been known to given us the exact nature of the potential value of the barrier potential. We say this is actually, this come under the, this is called, we call this as potential barriers. So now you just come to know what is the importance of this. Now what the Bloch is the name of the scientist, you will come to know in the later section. See what the Bloch says. Again, this has been different scientists which has given us the information regarding the movement of the electron. So we say that the electron is moving in the form of wave. So how mathematically he has given us the information regarding the movement of the electron. So the movement of the electron is given by psi of x is equal to uk of x into exponential of ikx. That is called what you can say the equation which signifies mathematically the movement of the electron. So now this movement of the electron is given by this particular function and this equation, where he says that uk of x is nothing but we can write uk of x plus a. That is called Bloch function, where a is known as, I just told you that a is exactly the lattice constant of the crystal. So when we just write an equation, whenever we write an equation, so what will happen is that definitely this is a this particular equation, we talk about Schrodinger equations. So that Schrodinger equation, so definitely in mathematics when we write a differential equation, it will have a solution. We need to consider that solution. That solution has been simplified for you. We only in the Kronig-Penny model deal with the important postulates which has been derived by Kronig and Penny. We discuss only the important postulates of the solution which has been given by the Kronig and Penny regarding the energy of the electron. So cos k is equal to p sin alpha. So what they say is that this is the, after complete simplification of the differential equation, we see here depending upon the Kronig Penny model that they say that the electron is moving in a square well, like a square well, right? So now that particular has been that particular geometrical view has been given by Schrodinger. A mathematical equation is given. So that mathematical equation I will have a solution, and that solution will be, when simplify it, and after simplification it will give us the exact energy value. So that is called possible energy value, what we obtain after different applications or different manipulations which have different what you can say mathematical operation. No, I should not say manipulations, but different mathematical operation, some calculation part, and that is a calculation part is very trivial. So we need not to go for that calculation part. So only the exact solution what we obtain at last, that cos k is equal to p sin alpha a by alpha a plus cos alpha a, where actually p denotes the potential, what you can say scattering power of the potential barrier. So a square well is nothing but you call that as a potential well. right? So that is given by mathematically 4 pi square ma v naught omega by h square, and the alpha value is been given as 2 pi by h under root 2 me. Now this is the values which has been obtained after calculating the differential equation, and this values you need to remember it, you have to practice it. And definitely the when we talk about cos or sine, the permissible value of cos and sine lies between -1 to +1. As you know that when we talk about the figure, you find that there is a v naught here. So here we find that v naught is a potential, and the w is the width of the barrier. So the width of the barrier is given by omega, you can say. So and v naught omega remains constant. So P is the scattering power of the potential barrier, or we'll say that that is the barrier strength. So now with this with this we just say that we have just given. So we thus say that this is the actual value what we obtained for this v naught omega, that is called barrier strength. And the what are the conclusion which has been made by the Kronig and Penny after writing a particular what you can say the solution what we discussed. You see, the previously we just discussed about the solution. Cos k is equal to p sin alpha a by alpha a plus cos alpha a. Now this solution, by seeing this solution, what the Kronig and Penny model says that the movement of the electron, you can just see the schematic figure here also. So the movement of electron in a periodic lattice. When I say periodic lattice, why I am telling periodic lattice? Why? Because the atoms or molecules or the ions arrange inside the crystal in a this particular format that is called periodic format. So periodic lattice is characterized by allowed energy bands and separated by forbidden regions. So Kronig Penny model says that whenever the electron is right traveling inside the crystal, it will adopt the character of the crystal. When it is adopting the character of the crystal, definitely when it is see, you can just see this figure, see this arrow mark, the electron is moving here and it is reaching to the minimum point, and when it is reaching to the minimum point, you will find there is loss of the you don't find any energy in this particular, see, this is the empty space. So this is called forbidden band. We'll say forbidden region or forbidden band, where the electron certainly is, we don't see the electron at this particular instant. So therefore it has been indicated with this particular region. White, you can just see this particular region is called forbidden region. So again, after some time, see some discontinuity, again the electrons start move to the maximum extent, and this process is, see, again this is again you find this particular value where you don't find the electron there, and empty space will be there. So like this will continue. So the movement of the electron in the metal is we say that the movement of electron in a periodic lattice is actually characterized by the allowed energy band, and they are separated by the forbidden regions. Now this forbidden regions you can just see, which has been indicated with the empty white spaces. You can just say this is the spaces, and here we have just taken, see, alpha a value we have taken on x-axis. This is very important aspect, and the p sin alpha by alpha a cos alpha. From where I have taken this? See here, cos k is equal to p sin alpha a by alpha a plus cos alpha a. So what we have taken here is, on the x-axis we have taken an angle value that is called alpha a value. Why? Because when we talk about an angle theta, right, so that theta is actually, it may be cos theta or sin theta. You can just see sin alpha a, cos alpha a, here cos k. So right, so here k indicates the wave vector. The characteristic of the vector is known by the factor called the wave vector k. So has the value of alpha a, see, if I increase the value of alpha a, the width of the allowed energy, you can just see the width of the allowed energy band is increasing. You can just see, when you see this this particular block where the energy is slowly, the width of this energy is increasing. You can just see this energy is increasing, right? Here the energy has been increased twice, thrice, and so on. So here I have see this forbidden band or forbidden region has been shown with the arrow mark here. You can say that wherever you don't find the electron, discontinuity of electron is there, or the energy of the electron is minimized, so you will say that is called forbidden region, or we simply say forbidden band. And here you get an allowed energy band, and -1 and +1, you can just say -1 to +1, this is alpha A. Now if the potential barrier strength, you see, if we increase this p value, see, if we increase the p value further, so what will happen, the function can be what you can say crosses the function. Now this if we increase it and this value of p is increased, then definitely the p will become very large, and it is the function at the right hand side. So you can just see that it will crosses +1 and -1. So why it has been taken +1 -1? Because the angle will change from positive to a negative value, that is +1 to -1. So thus we can say the allowed energy band become narrower, and the forbidden band becomes wider. And that figure has been not shown to you here. Simply it indicates that the band width will be what you can say inverse. Here the bandwidth is increasing. You can see there, if I increase the value of p very large, not infinity, it is large, right? So large, then the value of this you can see this figure where the +1 and -1, it has been increased from +1 to -1. So that when this is happening, the allowed energy band become narrower, and the forbidden, say the empty spaces, the width of the empty spaces or the forbidden band will be increasing. Now if the p is tending to 0, if we further improve, we say in the third point, if p is very large, in the next level, if I increase the value of p further, that is tending to infinity, then the allowed energy band is reducing to a single energy level. You can just see p is infinity, the allowed energy band reduces to one single energy level. So you can just see this particular waveform will go. Only you will find a vertical line which is crossing the positive value and the negative value. Now, so at last, if p is tending to 0, after infinity, it is tending to 0. So if p value is 0, then there will be no energy level existing, and the particle is free to move. So as we say that if I change the value of p from 0 to infinity, we find that completely free electron is becoming the bonded electron. So p is equal to 0, what will happen? The electron is free. P is infinity, it is getting bounded. So therefore we say that free electron is completely becoming bounded when we change the value of p from 0 to infinity. Now this is the conclusions which has been made by the Kronig and Penny. So in the next class, we just see in the today's class, we just had an introduction regarding the classical free electron theory, and also we just discussed about the different defects of the classical free electron theory and merits application. See what we have studied in today's class. We just studied in today's class the first of all, what is the free electron theory or classical free electron theory, which has been proposed by Drude and Lawrence, and what they say is, see, whatever the assumptions they made, so with that assumptions there were some applications, we got some advantages, and definitely we got some disadvantages also. So now that has been again, this was been assumed by Drude and Lawrence, and again the two scientists, Kronig and Penny model, says that when the electron is moving inside the metallic crystal, actually according to them this is happening, right? They concluded, so that conclusions we discuss here. So in the next class we just start again with the Kronig Penny model conclusion, last point. Again we'll have a very brief introduction of this Kronig Penny model conclusion, then we'll go for the an origin of energy bands in solid. What is actually the energy band in solids, and how the solids have been classified into metal, semi-metal or insulator. So now that definitely we'll discuss in the next class, and if you have any doubt regarding this particular class, definitely I will brief it up in the coming class, the next class. Then again we just discuss very briefly regarding the classical free electron theory and the conclusions of the Kronig and Penny model. Again we'll go over for the next topic, that is origin of energy bands in solid. With this I'll take a leave now. Thank you everyone. Thank you for your patient C, right. So with this just stop my talk in today's class. So in tomorrow's class we will discuss about the origin of energy bands in the solid.